In the last video, we saw the notions of supremum and infimum of sequences of real numbers. So let us now see the exercises of this section. So in this one, we have to verify the claim in example 4 of this section. In example 4, the sequence that we had is this sequence. And it was mentioned there that the supremum is 1 and infimum is 0. We need to justify those things, those statements. We have an equal to 1 over n for positive integers n. For all, I am just simply writing for, it means for all n greater than or equal to 1. Okay. Now clearly, one is greater than or equal to an for all n greater than or equal to 1. That is because 1 over n, when n is 1, 1 over n is 1. Otherwise, it is strictly smaller than 1. 1 over 2, 1 over 3, all of these real numbers are strictly smaller than 1. Thus, 1 is an upper bound of the set which, if you want to see the elements, we can also write the set in roster form like this. So 1 is an upper bound of this set, which one can also see from here directly. Let y be a real number such that y is less than 1, then y is less than 1 and 1 is a1, and hence y is not an upper bound of A. So what we have shown here is that no real number less than 1 is an upper bound of A. Equivalently, all upper bounds of A are greater than or equal to 1. Hence, all upper bounds of A are greater than or equal to 1. So that's why 1 is the least upper bound, because all upper bounds are greater than or equal to 1, and at the same time 1 itself is also an upper bound. Thus 1 is the least upper bound of A, that is supremum of an is equal to 1. So supremum of this sequence is 1, that has been justified. Now we need to prove that the infimum is 0. Since every element, infimum is 0. To actually apply the definition of the infimum, we need minus a. Next, minus a is this. Minus a by definition consists of the negatives of the elements of A. Okay. Since all the elements of minus A are negative, zero is an upper bound of minus a. Clearly, because you take any element, that element is less than 0. So 0 is an upper bound of minus a. We want to show that 0 is the least upper bound. So let us take some number z less than 0, or in fact let us be more specific. Let z be a real number such that z is less than 0. Then minus z is greater than 0, and we can choose a positive integer n such that n is greater than 1 over minus z. If minus z is greater than 0, 1 over minus z is also greater than 0, but no matter what this real number is, we can always find a positive integer n that is still greater than that real number, and this is possible because of a result that we have already come across. I can't remember the place exactly, but it is that result which says that if we are given a, was it about real numbers or rational numbers? If we are given a real number x, then there exists exactly one integer n such that these inequalities are true. In that result, a part says just this, that you can always find a positive integer greater than any given real number. You fix a real number, you always get a positive integer greater than that. Which is, which can also be concluded from the Archimedean principle. Yeah, that way also you can think. So we will always have a positive integer like this. Now what does this mean? It means we can first of all take reciprocal, because n and 1 over minus z are both positive. If we do that, the inequality will get reversed. Or now if we multiply by minus 1, we get minus 1 over n, and again the inequality will get reversed. This is greater than z. So z is not an upper bound. Not an upper bound of minus a. And why is that so? That is because we have obtained one element minus 1 over n that clearly belongs to minus a, because n is a positive integer which is greater than z. So how can z be an upper bound? Not an upper bound of minus a. That means what? 0 is an upper bound of minus a, and no real number less than 0 is an upper bound. In other words, all the upper bounds of minus a are greater than or equal to. In fact, let's just write that too. Thus, all the upper bounds of a are greater than or equal to 0. This implies 0 is the least upper bound of minus a, or we can directly write supremum of minus a is equal to 0. Hence, but our aim is to find the infimum of a. So infimum of the sequence an is equal to, by definition, that is nothing but the infimum of a, and that again by definition of infimum is minus of supremum of minus a. So this is equal to 0. So that's how we know that the infimum of the sequence of reciprocals of positive integers is 0. So this completes the solution. Then the second one, prove proposition 636. Hint. Use theorem 6 to 11. Okay, we will now first have to recall the statement of this proposition, and since we will actually use this theorem, so we need to recall that also, and then we can solve the exercise. Proposition 636 is this. We don't need to actually write the entire statement properly, we just need to see what it says. So an is a sequence of real numbers, and X is defined to be the supremum of an. So that is given. If m is an extended real number and is an upper bound of the sequence, then x must be less than or equal to m. That's one thing. And then if okay, but besides this, actually before this there is something else. Let me write the things in order, otherwise it will confuse us. Then an is less than or equal to x for all integers n greater than or equal to m. Then if the extended real number m is an upper bound of the given sequence, then x must this is x. Now x must be less than or equal to m. And finally there is something else also. If y is an extended real number such that y is less than x, then y is less than an, and an of course is less than or equal to x, that we already have from here. For at least one n greater than or equal to n. So this was proposition 636, and this theorem 6 to 11 is of course something we have already seen and we have proved also. Let E be a subset of the set of extended real numbers. Then these statements are true for any x belonging to E infimum of E is less than or equal to x and x is less than or equal to supremum of E. B. Part B is if M is an upper bound, M is an extended real number. If this is an upper bound of E, then supremum of E is less than or equal to M. And part C is about lower bounds. If this is a lower bound of E, then M is less than or equal to the infimum of E. Okay. Now we need to prove this using this. So let us see what we have. We have a sequence of real numbers and x is the supremum of this sequence. Then x is what actually? X by definition is the supremum of this set. So we can treat this set as E. Then by part A of this theorem, what does this say? It says that for any element in E, that element is less than or equal to the supremum. And now our set E is this, so any element in this will be An. So An is less than or equal to the supremum of E, that is x, for all elements, for all n greater than or equal to m. That means An less than or equal to x for all n greater than or equal to m, that we are directly getting from part A. Okay. Then in part B, if m is an extended real number and is an upper bound of this sequence, that just simply means that m is an upper bound of this set E. So by part B, supremum of E should be less than or equal to m. That means x should be less than or equal to m. And that is the second statement. So we can start the solution like this. the first two claims of proposition 636 follow from parts A and B of theorem 6 to 11. Okay, which is direct. You don't have to do anything else. You just look at these statements, look at what is being used from this theorem to conclude them, and you can directly conclude them. Okay, so this half of this proposition is over. Now we need to prove the last part. So we now have y belonging to R star such that y is less than x. We then have to prove that this happens. Okay, so let us see. That y is less than x. We need to prove that y is less than at least one element in the sequence. To the contrary, suppose that is not the case. Suppose an is less than or equal to y for all n greater than or equal to m, then y is an upper bound of the sequence that means of our given sequence. So y is an upper bound means you can think of y in place of m here, and we have just now shown that in that case x must be less than or equal to m. So by what we have concluded above, x must be less than or equal to y. But we already have y less than x, and this is a contradiction. But what is being contradicted? The fact that the order relation on R star satisfies this property called trichotomy. That is being contradicted because y less than x and y greater than or equal to x cannot be simultaneously true. So we need to specifically write that that result is being contradicted. This contradicts proposition 6 to 6 part D, that is the trichotomy. So that means our supposition is wrong. So our last supposition is wrong. That is, there exists an integer n greater than or equal to m for which y is strictly less than an, and an of course is less than or equal to x. So this completes the solution, and hence it also completes the proof of this proposition. Then exercise 3, prove proposition 6.3.8. Hint: use proposition 636, that means the one we have just now proved. Together with the assumption that the sequence is increasing, to show that the sequence converges to the suprema. Okay, so let us first recall this one, the statement. So here this is an increasing sequence of real numbers. That has an upper bound some upper bound is there which itself is a real number. A finite upper bound. Then the sequence is convergent and in fact the limit of the sequence is its supremum. Okay, so we now need to prove this. So let us start the solution. Since has a finite upper bound, let us denote the supremum by something x, say. So the supremum of the sequence is a real number. It must be because supremum is what? You take all the elements or all the terms of the sequence, form the set consisting of those things. The supremum of that set is defined to be the supremum of the sequence. So that set obviously is a non-empty subset of the set of real numbers, which has a real upper bound. So by the least upper bound property, the supremum of that set will itself be a real number, and consequently the supremum of this sequence, which is the same as that supremum by definition, is also a real number. So x is a real number, and x is what? X is the supremum of this set. Okay. Now we are going to have to show that the limit of this sequence is this supremum or x. So naturally we start by choosing any real number epsilon that is positive, since okay, do we need to again write this because we have just now written that x is the supremum? Then by proposition 6.3, this one is 6.3.8, so that one was what? 6.3.6. By proposition 6.3.6, we have x minus epsilon less than an for some n greater than or equal to m. What have we written here? You see, we have proved this last part of proposition 6.3.6, where we had this. Just like there, here also x is the supremum of the given sequence. Now, if we choose a number, an extended real number y that is less than the supremum, then there exists at least one term or one element in the sequence that is strictly greater than y. This y here is x minus epsilon, because epsilon greater than 0 means x minus epsilon is less than x, and this x is the supremum. So at least one term of the sequence should be greater than x minus epsilon, and the level of that, the index that gives us that term, let that index be n. N clearly will be greater than or equal to m, because that's where the indices are coming from. Okay, now we use the fact that the sequence is increasing. So an will be less than or equal to an plus 1, which will be less than or equal to an plus 2, and so on. Since this is increasing, we have less than an for all n greater than or equal to n, because the higher the value of your n is, small n is, the more you have the value of the sequence, or it may stay the same but it will never go below an. So automatically, since all these ans where n is greater than or equal to n are greater than or equal to an, so automatically all of them will be greater than x minus epsilon also, because an itself is greater than x minus epsilon. We thus have x minus epsilon less than an, and an is less than or equal to x. This again is coming from proposition 636, where we have proved that every element of the sequence, of any sequence, is less than or equal to its supremum. And if we add epsilon to x, then it will increase. So x is strictly less than x plus epsilon for all n greater than or equal to n. Equivalently, now you concentrate on x minus epsilon, an, and x plus epsilon. So x minus epsilon is less than an, and an is less than x plus epsilon. So equivalently, in fact, let's just write one more step. Minus epsilon is less than an minus x, and an minus x is less than epsilon. Or, in fact, let's show the variation of n2, or this is less than epsilon for but this is the condition that we need precisely to claim that an converges to x. Hence, limit of an is equal to x, which is nothing but the supremum of the sequence. And in this final equation, that part is also included, that an is convergent, because otherwise this has no meaning. Writing this does not mean anything if an is not convergent. So this completes the proof of proposition 638. And we will use this quite often. Whenever we come across an increasing sequence or a decreasing sequence, we see whether it is bounded or not. If it is bounded, then it's convergent, otherwise it's divergent. And finally, we have this exercise. Explain why propositions 6, 3, 10 fails when x is greater than 1. In fact, show that they are saying what we need to show exactly in order to say this, that this thing fails. In fact, show that the sequence x to the power n, where n varies from 1 to infinity, diverges when x is greater than 1. And in fact, to do that also, hint is given. So we are given almost the entire solution is given. Prove by contradiction. So that's why often it's not a problem at all. Although you see that most of the statements in Gauss analysis are, we are asked to prove them in the exercises, but very often ample hint is given to us. So usually it's not a problem. Contradiction and use the identity one, and also the limit laws in theorem 6.1.19. Further, compare this with the argument in example 1, 2, 3. So in example 1 to 3, if you remember, it is that place where we began everything by showing that if we carelessly use many of the rules of calculus, with which although we are familiar but we may not know them, or rather how to apply them or use them properly, can lead to nonsensical conclusions. So it is one such thing that we saw back then when we were discussing these examples, that we erroneously concluded that this limit is always did we conclude it is equal to 0 when x is not equal to 1, something like that? Yes, this is equal to 0 when x is not equal to 1. We applied some sort of argument when we discussed this example, and there we saw that whatever x may be, if x is not equal to 1, then limit of this is 0, which is not true. That's what we are going to show here now. The limit does not exist if x is greater than 1, so how can it be 0? So in this exercise we are being asked to show how this compare these two situations. Here we are saying that the limit does not exist, here we are saying that it exists. So what went wrong? We need to find that. Can you explain the flaws in the reasoning? In that example, okay. So we have been asked to show that this sequence diverges when x is greater than 1. Contrary to that, let us suppose that it is convergent even when x is greater than 1. Let there be a real number x greater than 1 for which the sequence x to the power n converges to some real number L. Okay, so this is our supposition, and we are now going to show that this leads to problem. Since so x is greater than 1 means x in particular is also a positive real number. So if we take reciprocal, we will have this 1 over x lies between 0 and 1. So because that is the case, we have but we need to refer to the results that we are using here by propositions 6, 3, 10 and theorem 6, 1, 19. Okay, what do we have? 1 is equal to limit of 1. Now in place of 1 we can write this, and that is equal to, okay, I should have written it not in this manner but like this. Okay, let us now justify the steps. 1 of course is limit of 1. Now in this equation you should interpret this 1 as the constant sequence 1. Okay, all of whose terms are equal to 1, and clearly that sequence converges to 1. We already know that. We have seen that any sequence consisting of the same real number, all of whose terms are equal to that real number, is convergent and it converges to that real number. So that is the first step. Now in this step we are just simply replacing 1 with this, which is true. Note that x is not 0. So 1 over x is meaningful, and that's why this thing is equal to 1 to the power n. And we have of course also used the elementary properties of powers of real numbers. Okay. Now in this step, this limit is the product of these two limits. That's where we are using theorem 6.1.19, where we have the limit loss. And why are we able to use that? That is because you see here we have two sequences. One of them is this, and the other one is this. We know that this sequence is convergent, and that is coming from proposition 6.3.10 and these inequalities. In proposition 6.3.10 we have proved that if y is a real number that satisfies these inequalities, then this limit is equal to 0. So think of 1 over x in place of y. So we know that this sequence is convergent and its limit is 0. And we have supposed that this sequence is convergent to some real number L. So limit of the product of these two sequences is equal to the product of their limits. And this is equal to 0, this is equal to L, so 0 times L is 0. But clearly this is nonsense because 1 is not equal to 0. This is an absurdity and proves that our supposition is wrong. So the way we actually our supposition is this: let there be a real number for which these things happen. So that means there is no such real number. So this is divergent for all real numbers x greater than 1. I am writing real numbers specifically because now we also know about minus and plus infinity, and we are here and there using them as extended real numbers. So we need to say that this x is not plus infinity. So that's why we are writing x is a real number. But the solution is not over yet. We need to also now say what went wrong in that example 1, 2, 3. In example 1, 2, 3, the mistake was the assumption that this limit exists for all real numbers which is not true. That's what we have shown here, specifically for those real numbers that are greater than 1, x to the power n is not convergent, it is divergent, so that limit does not exist. Let us also quickly recall what we did there. What we did there is this: we saw that this identity is true for any positive integer n. Then, without thinking of anything about convergence or divergence, we just simply mechanically took limit on both sides. And then this limit is L. This limit, of course, can be written as x times limit of x to the power n, because x is independent of n, and then we somehow concluded that because when a sequence converges to something, removal of one term from the sequence does not affect the convergence and the limit stays the same. So we assume that since this limit is something, it is L. So this is also going to be L. And then from here, of course, we have L times 1 minus x is equal to 0. And this implies L is equal to 0 if x is not equal to 1. So that's the conclusion we had, we made back then. But the mistake is here itself in the very assumption that these limits exist for any real number x, which is not true. So that's where we made the mistake. Okay, now this completes this set of exercises. And after this we have the next section, limit superior, limit inferior, and limit points of a sequence, which of course I will not do today, but let us just see at least something from that section. Let us consider this sequence whose terms are like this: minus 1.01, 0.001, minus 1.01, 1.001, and so on. You can see that the terms follow some pattern. Neglecting the plus and minus signs, you have 1.1, and then the ones are getting further and further away from each other as the number of zeros between them increases, and the terms in the sequence are alternately positive and negative. Now if you draw these things on the numbered line, they will roughly look like this. Say you have 0 here, and without being specific, let this be 1 and this be minus 1. If you look at the first term, just to show that to not clutter the space by actually putting the points properly. So say this is 1.1, then you have minus 1.01. Minus 1.01 is slightly more negative than minus 1. So say it lies here. Then 1.001 is more positive than 1 because you have 0.001, but less positive than 1.1. This more positive and less positive, these are not precise mathematical terms, but just for the sake of our understanding I am just saying it. It is suggestive, and you can clearly see what I am trying to say here. Then you have minus 1.0001. So that is more negative than minus 1, but less negative than minus 1.01. And then this one will be even closer to 1. So you can see that in a vague manner we can say that half the terms of the sequence are lying to the left of minus 1 and half of them are lying to the right of 1. Um, mhm. So the sequence clearly is not converging to anything. It is not even a Cauchy sequence. Uh, that is because, first of all, okay, it is not a Cauchy sequence because of this simple reason that no matter how far you go down the sequence, there are always terms in the sequence that are far apart. Okay, for example, the sequence is not eventually one over 2 steady. You cannot find a stage such that after that stage the difference between any two terms of the sequence is less than or equal to 1 over 2. That is not the case. So it is not a Cauchy sequence and consequently it is not convergent. But it seems like part of the sequence is trying to converge to 1. If you look at these terms that are positive, they seem to be coming closer and closer to 1 and they seem to be converging to 1. Just like that, the negative parts, all of them are less than -1, but they are also getting closer and closer to -1. So the sequence as a whole is not getting close to anything in our usual sense of convergence, but parts of it are getting accumulated somewhere. So we say that -1 and 1 are limit points of the sequence, of this above sequence. We need to precisely define this concept, and then there is something else. Limit superior or upper limit and limit inferior or lower limit of a sequence of real numbers. After defining this and after having some illustration in some examples of this concept, we will then define limit superior and limit inferior, and then we will see that when these quantities limit superior and limit inferior are finite, because we will see that their definition allows them to be infinite also, in the sense that they can be plus or minus infinity. We will see those things, but when these quantities are finite, then this turns out to be the greatest possible limit point, and this turns out to be the smallest possible, least possible limit point. And from the properties of these things, limit superior, limit inferior and limit points, we will be able to show that every Cauchy sequence of real numbers is convergent. So far we have only shown that every convergent sequence of real numbers is Cauchy, but using the techniques, tools and techniques of this section, the next section, we will be able to show that the converse is also true. Cauchy sequences of real numbers are also convergent, and after proving that, only the construction of real numbers from rational numbers will be fully justified. It's because of this thing we have done all this. Otherwise, we would have been happy with only the rational numbers. But in the sequence, in the set of rational numbers, if you consider a Cauchy sequence, there is no guarantee that it will converge. And since we need Cauchy sequences to converge in order to do calculus, that is, in a Cauchy sequence, roughly what happens? The further you go down the sequence, the distances between any 2 points of the sequence, they are decreasing. So we feel that they should get accumulated at some point, that is, there should be a limit. That thing is not true in the system of rational numbers. That's why we say that the rational number system has gaps or holes in it. So we fill those gaps in the system of real numbers, and this is where we show that yes, the gaps have been filled. And so you can model it as a continuous line, a continuum. And this idea we will see in functional analysis also, where we have Banach spaces and Hilbert spaces. If I say this, it may make some sense. This idea that we are seeing here of completeness of a metric space, that idea here is happening in only one dimension. You increase the number of dimensions, then you get Banach and Hilbert spaces. In some sense, we will see why. Okay, so these things we will do in the next video. So let me end the video here itself today. If you have anything to say about these things, then you can write in the comment section below, or you can mail me also. Since I haven't written the address recently, let me write it here. Here. So we are slowly but steadily going ahead. One day these things will be over, and we will then be entering calculus. That is the things that calculus has, the central things, continuous functions, derivatives, integration, all those things. And when we finish those things, we will see that sequences are very important, because the kind of space we usually do calculus in, they are a special type of space. When that speciality is not there, then sequences lose their utility. In such spaces where sequences are no longer adequate for some purposes, we will see sequences are replaced with something else, nets and filters. Okay. So anyway, so let's just wrap this thing up, and let's not go ahead of ourselves. So this is me, Lucifer, from a mathematical room. See you in the next video. Have a nice night.